Yeah, this is the topic of my talk. Let's start about what are free-surface flows that are CFD problems where a large portion of the fluids is unconstrained, and so it's free to evolve during the simulation. And this kind of flows has particularly challenges since the fluid domain, the computational domain, evolve and has to be computed as a part of the solution, frequently resulting in complex evolving geometries. Numerical methods for this kind of fluids as to account these challenges, and are typically divided into two main categories. On one side, we have Eulerian methods where the computational mesh is fixed, but to track the free surface, this method required particular tools. For example, volume of fluid and level set method are two examples. And for volume of fluid, we have a scalar that account for the percentage of fluid that there is in a particular cell. Or in level set method, we have a level set function that is positive inside the fluid and negative outside, and is 0 on the free surface. On the other side, we have Lagrangian methods that are particularly effective because they naturally track the evolution of the domain, but a great challenge for Lagrangian method is the fact that during the simulation the mesh can deteriorate because it moves, and bad elements could appear, and it becomes difficult for the numerical method to converge and to have accurate results. And therefore, a possible choice is to have particle methods that discard the mesh and consider the simulation as an interaction of particles. And this creates another characterization that is mesh-based against particle-based method. Our research group focuses on a Lagrangian mesh-based method that account for the challenges about the mesh with an efficient remeshing technique. Basically, we discretize the domain as in particles method with a set of particles, and we create on top of that particles a mesh with this remeshing technique. Then we solve the Navier-Stokes equation that are the governing equation for the fluid mechanics with the standard finite element method, and move the nodes accordingly. And whenever the mesh becomes too distorted, we discard the connectivity between the elements and we recreate the mesh. And we time loop on this, updating both the solutions field and the domain shape. The particle finite element method has proved to be effective to simulate also real industrial scenarios. For example, this is a numerical simulation of a 3D concrete printing 3D concrete printing example from our colleague Giacomo Rizzieri that focused on this topic. And as you can see, a big problem of numerical simulation is the fact that simulate this kind of problem can become very computationally expensive. And this is an 8-layer simulation, and as you can see here, for real To create a real object, we would need hundreds of layers of simulation, but we need 12 days only to simulate this. So to scale up to real-world scenarios, we need faster simulation. And the standard reduced order method approach often faces problem with evolving geometries. So the idea is to use machine learning to create surrogate models for this kind of problem. Machine learning-based surrogate models for numerical simulation can be divided into two categories. On one side, we can reconstruct the whole dynamics of the problem. And for us, it means to reconstruct the velocity and pressure field at each time step. This is, of course, a really complex task for a machine learning algorithm because it means to learn the mapping between infinite dimensional spaces. And therefore, our idea is more to go through an hybrid model that combine a surrogate model and numerical model to use the surrogate model only in the portion of the domain and in the times where it is reliable, and to solve the rest of the problem numerically. To do that, the structure of the surrogate model must be as similar as possible to the numerical scheme to be coupled. On the other side, we can only reconstruct some feature of interest of the simulation. For example, some stresses, some forces, or the shape of the domain or the free surface. This is, of course, a much simpler problem because we focalize only on one task, but it required to train new models for each task and often to develop a new architecture for the neural network for each task, because maybe there are some differences in what we wanted to learn. Of course, if we have the left kind of models, we can infer this kind of feature of interest from the whole dynamic. We are trying to do both of these approach with neural PFM and ShapeGen 3DCP that is specific for 3D concrete printing. Let's start from neural PFM. The idea is to keep exactly the same structure of the numerical solver and to replace at each time step the time advancement with an autoregressive neural network. Autoregressive means that it learns the time advancement of the system and is then recalled repeatedly. We want to keep the mesh-based approach of the PFM to both for the coupling, for a future coupling with the PFM, and to be able to reconstruct the variables, the derived variables. The idea is that this model is trained by predicting, given a current state of the system, to predict the next one and to compare it with the reference PFM simulation, and then to update the weight of the neural network through backpropagation. And in this way, the neural network learns by trials and error to increasingly reconstruct the solution field. Inside this black box, we can put different architectures. We started by considering graph neural networks that are a natural choice for mesh-based approach, because a mesh can be seen as a graph, and the graph neural network compute the interaction between nodes by aggregating information through connected nodes. And we are recently moving to another kind of architecture that is self-attention architecture that instead does not consider the edges that connect the nodes, but compute and learns the interaction between different particles through a score that is learned as well during the training. And this consent to reduce the number of data that must be stored to training the network, and therefore to be lighter on the GPUs, because the graph neural network are very memory consuming. Let's see some results. We started from Newtonian fluids to Newtonian fluids, where we change in the dataset, in the training dataset, only the starting, the initial geometries. And this is a sloshing example. This is a result on an unseen simulation. So this simulation was not in the training dataset, and we are able to reconstruct it very well. And as you can see, we can also from the solutions fields, we are able to reconstruct also derived quantities as forces acting on the wall quite accurately. This is another example with a more complex fluid. This is a Bingham fluid that acts as a solid up to a certain level of stress, and then start to flow like a fluid. And this is the kind of problem that we consider. It's like a landslide, a simplified landslide. And in this case, in the training dataset, we varied the material properties of the material and the inclination of the plane. These are three different results on, again, unseen case. So this case were not in the training dataset. And we can see that the variable of interest, the main variable of interest, if you are considering a landslide that is up to where the runout that is up to where the landslide goes, it's very well reconstructed. And here we can see also the fact that attention version of the architecture, it's very less memory consuming with respect to the GNN, the graph neural network 1. Here we can see also another reason why we keep on using the mesh, even if, for example, in the self-attention version of our architecture, the edges are no more required, because keeping on using the mesh and considering the mesh, we can also exploit the mesh knowledge that we have already on the PFM. And so in the PFM, we have some tools that are able to keep the nodes distribution and the mesh quality high, while without using the mesh, the particles during the simulation tend to cluster and to go in a distribution that are no more uniform. And this is finally a 3D example. This is again a Bingham case. And this is a slump test that is a typical test for concrete. And also in this case, we trained it on different material properties, and we can see that the model is able to really reproduce the material properties of the simulation. And also in this case, we are able to reconstruct internal stresses from the solution fields. In all these example that I showed, I didn't put by purpose what is the reference and what is the reconstruction, because you can bet on it. Let's see now the second type of surrogate model. This is the architecture of the ShipGen 3DCP, that is a tool that we developed to predict from the material properties of a 3D printing scenario the cross section and so the free surface setting of the printed layer. And we generate a data set of almost 200 3D printing, and we parameterized the shape of the cross section through Fourier series, and we are able to reconstruct quite accurately and immediately the cross section of these shapes. So to conclude, I show you two different surrogate models for free surface flows, Neural PFM and ShipGen 3DCP. Neural PFM, that is that reconstruct the whole dynamic of the system, and ShipGen 3DCP that focalize on predicting the cross section of a 3D concrete printing simulation. For the next step, we aim to couple this surrogate with the numerical method, and to go through Neural PFM real-world application. Thank you for the attention.